Hello class, today I'm going to show you how we can simulate a natural convection problem. It is going to be a very easy one, but I think it's a good starting point. Let's start with workbench. Open FLUENT and click over geometry. I want to show you just very simple case 2D rectangular geometry. So let's let Ansys or FLUENT know that I'm working on 2D. Space claim is going to be opened and we can start drawing. Okay, the drawing plane is ready. A rectangular shape is going to be 18 by 18 millimeter. It's okay for me. Let's pull it, and when we click pull, it is going to automatically create a surface. Done with it. Open mesh. Okay, it's ready. Let's see what type of default mesh it is going to create for us. Pretty nice, uniform mesh, but the size is not interesting. So I'm going to first of all select method and tell Ansys actually I want you to use quadrilateral dominant. Yeah, this one. Also, I would like to control sizing because it's a rectangular. So all sides are selected, and instead of size, let's give it number of divisions. Maybe 200. And yeah, let's see the mesh quality. So as you can see, we have very fine mesh close to the wall and larger mesh at the center, which is good. But you remember from finite difference topic, when we have this type of very sharp mesh size change, so which we called it mesh expansion coefficient, when it's very large, the accuracy of our calculation is going to be one order of accuracy less. So we don't want this happen to us. So let's see what I can do. Let's go for sizing, and instead of coarse to go and select fine, and as much as possible let's go for the uniform. Hopefully it is going to decrease this mesh expansion ratio. Currently it's very high. It should be like a 1 point something, but we want to reach 1.1, 1.05, something like very close to 1. Okay, anyway, we can play with it. Let's add sizing, for example, for this surface, and say currently is 0.3, 0.2. Now it may get better. So if you want to have a more accurate result, play with the mesh, improve it, and definitely the number of mesh is going to increase, but the quality and the accuracy of your calculation is going to be much better. Okay, very good. I'm happy with this one. Now let's name the different parts. This is going to be my left wall, right wall, top wall, and finally bottom wall. So you can see these names here: left, right, top, and bottom. And the mesh is pretty good. Let me check the statics and the number: 12,000 nodes and elements. Okay, let's close it. Update mesh to make sure all the data is ready for setup. Double precision, parallel processing. Let's go with 4 processors and open Ansys FLUENT. Okay. For the solver, let's select pressure based. So pressure based solver, we don't want to have density based, because we have a plan to use business approximation, and density is going to be constant, and usually when you select density based, it's so time consuming. And steady state, I want to do just a steady state, easier and faster for me. But if you want, you can go for transient, and you know there isn't that much difference between them. You just need to adjust the time steps, because this is a natural convection example. We need to turn on gravity. Gravity is going to play an important role, and it's going to be at negative y direction. Let's go and check the model. We need energy equation, so I'm going to turn it on, and the type of flow. You need to check what type of flow we have. I haven't made decision what temperatures I'm going to select, but you need to calculate Rayleigh number. You have the dimensions of this box or domain. You know what temperature difference you want to select. The fluid or working fluid is going to be air, so you can easily calculate what is Rayleigh number. If it's under critical Rayleigh number, you can consider as a laminar. If it's above that, consider turbulent and select the turbulent flows. For simplicity, I'm just considering laminar flow. Let's go for material, open air. This is the air, and I'm going to consider ideal gas. You can go and consider incompressible ideal gas, but I'm going to consider just ideal gas, change and create. So one is ready. Also, this is aluminum. I'm happy with it. And also I want to create insulation, and the formula is going to be ins density. Let's go 50, for example. Specific heat is okay, and thermal conductivity, because in insulation it should be very small number, so 0.05 watt per meter Kelvin is going to be my insulation thermal conductivity. change and create, no there. So we have air as a working fluid, and these two, aluminum is going to be used for left and right side walls, and insulation for top and bottom. Basically I want to have zero heat flux at the top and bottom walls, and two isothermal walls at the left and right sides. Good. Let's check the zone cell zone condition. It's supposed to be air, and because I just have one fluid, automatically selected air as a cell zone condition. And let's turn on Business approximation. So gravity is here, operating temperature is this, and I'm going to turn on the operating density. So this is going to be our operating density for the working fluid, which is air here, and automatically Ansys knows, because we selected cell zone condition fluid and that fluid was air, it is going to put it here. This part is very important, otherwise you can't connect momentum equation with temperature or energy equation, and this business approximation plays a very important role there. What is it? Operating temperature. Let me change the unit. It's easier to work with centigrade than Kelvin. So let's go with 20 degree. Done. Boundary condition, bottom wall, so stationary wall, no slip condition, happy with this. And as I said, bottom wall and top wall is supposed to be have zero heat flux, which is automatically is there, but the material is going to be insulation material, which I already designed. And wall thickness, let's go with a small number like this, which is not going to be important. Top one, and it's same, zero heat flux, and wall thickness, and the material, the insulation. For the left wall, let's select, because it is going to be supposed to be isothermal wall, and isothermal wall is the wall with constant temperature. I'm selecting thermal condition as a temperature, and let's go with 30 degree. This thickness, and the material is aluminum. So left wall is going to be 30 degree. What was the operating condition? Okay, 20 degree. And right wall is going to be also isothermal wall, and with 20 degree, similar to the operating temperature, and the material is going to be aluminum. This is the 20 degree, and operating temperature is also 20 degree. So left wall is ready, right wall is ready, yes, and I already adjusted bottom and top walls. Okay, let's go and check the method. Second order, yeah, we are happy, nothing to change. Control, yeah, we are happy with the relaxation factors, and we keep it as a default. Monitor the residuals, usually the default one is 10 power minus 3. Let's go with 10 power minus 5. And energy is 10 power 6 minus 6. We are happy with that one. And for initialization, you can select hybrid one or standard one. I'm selecting standard one and say initialize for all zones. Okay, I also want to patch it, which means I want to specify initial condition. because operating condition was 20 degree, it is going to automatically consider 20 degree, but I want to make sure it is 20 degree. So let's put 20 degree temperature for where? For the middle surface, which is the liquid surface, and patch it. Did I initialize it? I don't know. Let's initialize. Okay. Let me read this warning here. For compressible ideal or real gas model with buoyancy, it is recommended to use the specified operating density value of 0. Okay, yeah. So it says go and select operating condition, the 0 for density. So I'm going to select that one, because I selected ideal gas, which is compressible. If I selected incompressible, we could specify a density. So let's initialize it again. Oh, I didn't select all zones. Now initialize. Let's go and run it for 600 iterations. Let's calculate. As you can see, energy equation converges very fast. It's under 10 power minus 3, minus 6. For the others, it takes a bit time to reach under 10 power minus 5, which we selected as a convergence criteria. But they are all doing very good and gradually reaching the level we asked. Okay, we finished the 600 iteration. Let's go and check the results. For the contours, I can go here. Okay, edit. Let's see the temperature contour for interior. Compute, display. As you can see, this is nice temperature gradient here. We have hot wall at the left, cold wall at the right side, and you can see we have this thermal boundary created here, and gradually they're going upward, and we have a thicker thermal boundary. Okay, let's check the velocity, magnitude, compute, and display. This is the velocity contour. And finally, pressure one. We have higher pressure at the bottom and lower pressure at the top, which we expected. So let's go back to the temperature. Okay, you may want to see a temperature for profile at this line, for example at the center, or at this line, or anywhere you want. So to see those values, you need to create some lines, or if it's 3D, some plans. So I'm going to create a line, and the line tool, as you can see, it is going to show us this is the line. I'm happy it's at the center. If you want to change the position, you can change these numbers. This is x0 and y0, which is going to be here, and x1 and y1, which is going to be there. And the name of that line is line number 5. Let's press create. Now I'm going to find temperature contour over that line. Oh, I made a mistake. It was a vertical line. So you can have, you can see this is the temperature profile over this line. Let me create another line, horizontal one, horizontally showing us the, okay, if I want to have this x supposed to be 0 and y should be this, and same y here. Let's call this one, for example, number 8. Create. And if I check the counter for this, let's put both of them. Now you can see we have profile, temperature profile over this, or velocity profile there. Okay, now let's plot. You may want to extract these data to Excel or anywhere else. So let's plot it. I want to find temperature over line 8. Plot it. Close to the left wall we have high temperature, gradually decreases. At the center it's almost flat, and then again decreases close to the right wall. You can consider the thickness from the right side to here as a thermal boundary layer, and from here to here right side, left side thermal boundary layer. Okay, so now I want to extract the data. If you click here, write to file, write, and go, I want to save it, desktop, number 12. Let's save it there. And I want to see what type of file is that. So this is the file we saved. Let me open it as a notepad, for example. And now you can see these are the temperatures we have for x, or distance from the left to right. Okay. We could have some vectors, for example, velocity vector for interface display. Let me go a bit larger, so it would be more interesting. You can see we have some circulation here at the center, and we have downward flow. Is it downward? Yes. And upward there, so it's kind of circulating. Okay, thank you very much. See you next time.